I'm Dr. V. Vijay Badi, Assistant Professor, PG and Research Department of Mathematics, Sri Sharda College for Women, Salem. Now I am going to take classical dynamics. First, introduction. Classical dynamics is a branch of physics that studies the motion of particles and rigid bodies under the influence of forces. Rooted in Newton's law of motion, it provides a framework for understanding mechanical systems from planetary orbits to engineering structures. Beyond Newtonian mechanics, it extends to Lagrangian Hamiltonian formulations, which simplify complex motion using energy based principles and generalized coordinates. Classical dynamics plays a crucial role in various fields, including astrophysics, robotics, and quantum mechanics, forming the foundation of modern physics and engineering applications. Now we are going to see Newton's three laws. Newton was one of the most influential scientists of all time. His idea became the basis for modern physics. He built ideas put forth from the works of previous scientists, including Galileo and Aristotle, and was able to prove some ideas that has only been theories in the past. He studied optics, astronomy, and maths. He invented calculus. German mathematician Gottfried Leibniz is also credited with developing it independently at about the same time. Sir Isaac Newton's three laws of motion describe the motion of massive bodies and how they interact. While Newtonian laws may seem obvious to us today, more than 3 centuries ago, they were considered revolutionary. So here we are going to see Newton's three laws: first law, second law, and third law. Now, first law. The first law says that an object at rest tends to stay at rest, and an object in motion tends to motion with the same direction and speed. Motion or lack of motion cannot change without an unbalanced force acting. If nothing is happening to you and nothing does not happen, you will never go anywhere if you are going in a specific direction unless something happens to you. You will always go in that direction forever. See this diagram. With no outside forces, this object will never move. It remains same only in same place. With no outside forces, this object will never stop. This object is moving with no outside forces acting upon it. It will remain go on the same direction with the same forces. This is called as Newton's first law. Next, we're going to see Newton's second law. The second law says that the acceleration of an object produced by a net total force is directly related to the magnitude of the force, the same direction as the force, and inversely related to the mass of the object. Inverse is a value that is 1 over another number. The inverse of 2 is 1 by 2. The second law shows that if you exert the same force of two objects of different mass, you will get different accelerations, changes in motion. The effect of the smaller mass will be greater and more noticeable. The effect of a 10 Newton force on a baseball would be much greater than that same force acting on the truck. The difference is effect is entirely due to the difference in their masses. So F equal to ma, the forces acting on it. Here, the more force, the more acceleration. So the figure, and we are easily able to understand the second law. Next, third law. The third law shows that for every action, there is an equal and opposite reaction. Forces are found in pairs. Think about the time you sit in a chair. Your body exerts a force downward, and the chair needs to exert an equal force upward on the chair will collapse. It is an issue of symmetry. Acting forces encounter the other forces in the opposite direction. There's also the example of shooting a cannonball. When the cannonball is fired through the air by the explosion, the cannon is pushed backward. The force pushing the ball out was equal to the force pushing the cannon back. But the effect on the cannon is less noticeable because it has much larger mass. That example is similar to the kick when a gun fires a bullet forward. So this example shows that for every action, there is an equal and opposite reaction. So these are the three main laws of Newton's law. These are very, very useful in classical dynamics. Next, we are going to see system of a particles. With respect to a system of three-dimensional coordinates, that is x, y, z dimension, we need 3n number of independent variables to describe the position of a system consisting of n number of particles. If there are k number of constraints means restriction, then we need only 3n k number of independent variables. We define degrees of freedom of the system as 3n minus k, that is 3n independent variables minus the constraints, that is restriction. That is called as degrees of freedom. By looking at the system, we can define these independent variables and they are called generalized coordinates and they are denoted by q1, q2, etc. qn. Next, we are going to see constraints. Constraints means we already know restriction. That constraints can be classified into two types. One is holonomic constraints and other one is non-holonomic constraints. How the holonomic constraints can be defined as they express the function of the space coordinates and time. For example, a rigid body length between any 2 points is called constant. This is called holonomic constraint. Example 2 shows that the non-holonomic constraint. For example, if you are considering a fluid inside a spherical vessel of radius r, if the distance between the center of the vessel and a fluid of a particle, then we have this is non-holo, then we have r less than or equal to a. This is called a non-holonomic constraints. Next, we are going to see degrees of freedom, which remains the number of independent variables required to the described of the system. After observing the system, one can define the generalized coordinates. Here, the simple pendulum is having this radius is theta taken as. Okay. Since system has one particle, need three independent variables. Constraints. What are the constraints for a simple pendulum? Particle moves in a plane. Next, length of the string is constant. This string is constant. Length of the string is constant. Therefore, we need 3 minus 2 equals to 1 independent variable. It has only 1 degrees of freedom. That is 3n coordinates minus 2 constraints here. They are given. Particle moves in a plane and length of the string is constant for a simple pendulum. So 3 minus 2 is 1 independent variable. So it has only 1 degrees of freedom. Define the generalized coordinates as the angle between downward vertical and the string. This is the example for degrees of freedom and the constraints. Next, Lagrange's equation. First result. Suppose Ri is the position vector of the ith particle and Qi is the jth generalized coordinate. Then we define dou Ri dot divided by dou Qj dot equal to dou Ri by dou Qj. Now we have to put first to take the generalized coordinates Ri equal to Ri Q1, Q2, etc. Qn, comma T. This is the independent variable. Dri is summation ij equal to 1 to n dou Ri by dou Qj into dQj plus dou Ri by dou T into dt. This is the total variation is the first equation. Next, therefore, Ri dot equal to dou Ri by dou T. So 1 by dt equal to, we substitute the result 1 here. We get, after multiplying this inside, we get this result. Hence, dou Ri dot divided by dou Qj equal to dou Ri by dou Qj. Next result. Dou by d by dt, dou Ri by dou Qj equal to dou Ri dot by dou Qj. Since we take the results, first Ri dot results, differentiate with respect to Qj. Here, both sides we Qj. Next, we are applying the dou Qj inside the term. So we get this result. And applying m equal to 1 to n summation, we get this result. Hence, the result is proved. We have dou Ri by dou Qj equal to dou Ri by dou Qj. This is the result one we already proved. Then second result is d by dt. Dou Ri by dou Qj equal to dou Ri dot by dou Qj. This is very important results in the classical dynamics. Next, we have seen kinetic energy of the system is T equal to half mv squared. Here we are taken generalized coordinates. So Ri dot dou T by dou Qj equal to dou by dou Qj. Instead of T, we substitute this value here. Next, multiplying dou by dou Qj inside the term, we get this results. So dou by dou T by dou Qj equal to summation this one. Also, dou T by dou Qj dot equal to dou by dou Qj dot equal to summation this results. So we multiplying this. Next, we get this results. Then here, by result 1, we can substitute dou Ri dot by dou Qj dot is equal to dou Ri by dou Qj by the result 1. Hence, dou T by dou Qj equal to summation I equal to 1 to n mi by Ri dot dou Ri by dou Qj. This is the result 3. Next, dou T by dou Qj dot equal to summation Ri dou Ri by dou Qj. Instead of using the result 1, we get the result 4 from the 3. For example, if you are taking the system of particles, change slightly without changing the time t, then equation 1 becomes this one. Work done by the force Fi dot dri. Here Fi is the external force of the ith particle. So here we get this results. Hence multiply this one. Qj is defined as by summation I equal to 1 to n Fi into dou Ri by dou Qj is called the generalized force associated with the generalized coordinate Qj. Also, work done by the forces is taken in the n generalized coordinates. So work done of Q1, Q2, etc. Qn gives us this one, j equal to 1 to n, dou W by dou Qj into dQj. Multiplying this on both sides, we get this results. Since dQj are all independent, above equation yields from the result of the equation 2, applying Newton's second law, that is Fi equal to mi into Ri double dot to the ith particle, we have Fi into dou Ri by dou Qj equal to mi into Ri double dot dou Ri by dou Qj. So we get the results multiplying this one into the inside of this one and subtract them. We get by the result 2, this one. Next Qj, we are applying the values, summation I equal to 1 to n Fi dou Ri by dou Qj. We get this result. Next, this one. When result 3 and result 4 are applied in the above equation, it reads as dou T by dou Qj equal to summation I equal to 1 to n mi Ri dot dou Ri by dou Qj. And similarly from the result 4, dou T by dou Qj dot equal to summation I equal to 1 to n mi Ri dot dou Ri by dou Qj. So we get the results. This called as the main results of the classical dynamics is Lagrange's equation of motion. Next, we are taking the special case. Suppose all the forces are conservative, there exists a scalar function called potential function. All the forces are conservative means then the scalar function is called potential function. That is V equal to V of Q1, Q2, etc. Qn, comma T. By the definition of the potential function, dou V by dou Qj dot equal to 0. Next definition, Lagrange's function L of the system is defined as the difference of kinetic energy and the potential energy are denoted by L. That is, L equal to Lagrange's function, T is the kinetic energy and V is the potential energy. Kinetic energy minus potential energy gives the Lagrange's function or Lagrangian. So dW equal to F dot D or minus del W into V into dr minus dV. Hence, by the equation 2, Qj equal to dou W by dou Qj, we get this results. And then applying the both results and multiplying and subtracting from the equations, we get T minus P. So taken common outside, d by dt. T minus P get taken to 0. Dou by dou L Qj dot minus dou L by dou Qj equal to 0. This is called the Lagrange's equation for the conservative system. Next, we take the example. A particle of mass m moves in a conservative force field. Find the Lagrangian on the equation of motions in a cylindrical polar coordinates. If you are taking the axis of O is at a O XY plane, this OQ equal to R. Here, three coordinates we are using x, y, z. We take in the x-axis or cos theta, y-axis or sin theta, and z-axis in the zk. So multiplying and substituting this value, we get the answer is L equal to half r dot squared, r squared theta dot squared plus z squared minus v of r theta comma z. Therefore, we have to, this is the L equation. We differentiate with respect to r dot theta dot z dot. Next r theta and z, we get this results and substitute in the value, we get the equation. M is a double dot plus dou v by dou z equal to 0. Next, we see the second example. Suppose that the particle in the previous example, we take the previous example, moves in the OXY plane and V equal to VR only if at that time t equal to 0, the particle on the OX axis of distance A and the velocity of the particle is V naught in the direction of the positive OY axis, find the velocity. Here, we have to find the velocity of the particle for the previous example. So we are taking the previous examples to become the equation like this. And then we substitute the c value r square theta dot equal to a v naught. Then we combine this one and multiplying equation. So the equation becomes the further, then the equation of the above particle becomes this and integrate on both sides. Next, we get the results of the and then the constant is half mv squared, that is half v naught squared plus 1 by m v of a. This is the previous example. We are finding the velocity of this, the previous particle of the examples. Thank you.